Okay, in our last video we just looked at some of the ways that cells use energy and store energy, and we looked at the energy shuttle ATP, but we're going to take a side step here and look at energy and kinetics. So we're going to look at energy profiles of reactions. So different biological reactions have different energy profiles, and they're quite descriptive of what's actually happening in a reaction. And then we're also going to look at some of the kinetics. It's important, I'll mention a few times through this video, that the energy changes in a reaction and the kinetics, or how fast a reaction goes, are actually separate considerations. You can have an extremely exergonic reaction, so something that releases a lot of energy out into the world and is spontaneous, but it can actually go quite slowly. So energy, or thermodynamics, is quite separate from the kinetics of a reaction, and that's important to keep into mind. So first we'll have a look at the energy profiles of certain reactions. So here we have what's called an exergonic reaction. So we'll just label the axes. So on the y-axis we have what's called delta G, and that is what's called the free energy of the system. So it's a complex thermodynamic quantity, but it's essentially the capability of a system to do work. So up here, when we have the reactants, we have a larger capacity to do work. Sorry, it's not delta G, it's just G. We have a larger capacity to do work, and then we release energy in this reaction and make the products which have less capacity to do work. So somewhere in here we've released energy, and if it's been coupled to something useful, done useful work, but done some work nonetheless. And this quantity in here is called delta G. So that it's the change in the free energy of for the whole reaction. And this reaction is called exergonic. So exo, like exothermic, and gonic, which means G. So exergonic, or releases free energy. So it's actually highly linked to the property of being exothermic, so releasing heat, and most exergonic reactions are exothermic. Because a lot of one main type of free energy is heat of a system, but not necessarily all. So, and this bump in the middle, we'll get back to that just in a second, but we'll move on and look at the opposite reaction. So in this reaction we again have G, and sorry, on the x-axis here we would have had time. So as time progresses and as the reaction progresses, and we have G, so free energy on the y-axis, and again time on the x-axis. And here we have our reactants actually having a lower free energy than the product. So work is actually required to change our reactants into products. So the system is absorbing energy. It is having work done upon it. So we call this endogonic. So this is where the system is during the chemical reaction, it's absorbing energy. Now you might have you would have noticed in both these they had little humps above the products and reactants. This is what's to do with what's called the activation energy, and it's actually a very important quantity when we start talking about kinetics. So the thermodynamics, or the energy change in a system, which is these delta G's here, no matter what you do, they're fixed. They're fixed for any reaction. However, this small hump you need to get over in both reactions here and here. To progress from the reactants, you need to go up an extra amount of energy to get to the products. That can be changed. That's called the activation energy, or EACT. So that's the activation energy there. And that's a very important quantity when looking at thermodynamics. So let's have a look at the next slide. So again, kinetics is not equal to energy. So the energy of the system is completely separate from the kinetics. But if you have a large activation energy, the speed of the reaction is going to be quite slow, no matter how big the energy changes. So you could have a reaction profile somewhat like this. So if we have G here, and we have our products all the way up here, and we have a huge activation energy, but also a huge, so here's our delta G, it's very big, but we also have a very large activation energy. That reaction is going to be quite slow, despite the fact that it is a large exothermic exergonic reaction. So, for example, an example of this is sugar combustion. Burning sugar is very exergonic and exothermic, so it releases a lot of heat and a lot of free energy. However, when you have sugar in a bowl, it doesn't spontaneously combust. It doesn't happen very fast. So you need to increase the temperature quite a bit to make it combust at a significant rate. Another interesting example of this is diamond decomposition. So actually diamond, the thermodynamics of the system are when you have a piece of diamond, the jewel, the system actually has a large energy preference to change the diamond back into pretty much graphite, which you find in pencils, and there's a lot, like, energy is released when this happens, so it's energetically it's preferable for the diamond to change into graphite, but there's a large activation energy, and so this process happens extremely slowly, and in fact diamonds do over billions of years turn back into graphite, but it takes an enormous amount of time because the reaction is so slow. So when we talk about kinetics, in biology we mainly talk about enzymes, and because they're the things that speed up reactions and they act as catalysts. So what they do to speed up reactions, pretty much they offer an alternate path for the reaction which has a lower activation energy. So you can see here our reaction profile. This is an exergonic reaction. We have this original activation energy up here, but then we have a lower activation energy given when the enzymes involved. So the enzyme will stabilize certain transition states and intermediates of the reaction and give a lower path for the reaction to follow with lower activation energy. And by lowering this activation energy, you actually speed up the reaction. So when you look at kinetics, you look at the different steps. So when we look at the uncatalyzed, the reaction with no enzyme catalysis, we just have reactant going to product, and we have a higher energy of activation. When we look at it with energy, with an enzyme catalyst, we have a reactant plus enzyme, and then it goes to an enzyme substrate complex, which stabilizes the transition states of the reaction. You don't need to worry too much about that, but it lowers the activation energy. It makes it more, it helps the reaction proceed, and that goes to enzyme plus product. And though there's more steps in the reaction itself, the reaction actually proceeds faster because of this lower energy activation, this lower energy hump you need to get over to proceed in the reaction. So enzymes, as I mentioned in the proteins lecture, other things other than catalysts increase speed of enzymes. So reaction rate is also increased by, well, catalysts, as we've mentioned, so that enzymes, but also reactant concentration. So the higher the concentration of the reactant, the higher the rate of reactions. So this isn't entirely preferable in biological systems because a lot of different compounds at high concentrations are poisonous, like even things like oxygen, which can do a lot of cell damage. So that this isn't a good system for a biological system. And also temperature increases the rate of reaction. There's a thing called the Q10 Rule, which is pretty much for every 10-degree raise in temperature in Celsius, you double the reaction rate. But again, we can see how this doesn't really work for biological systems because continually raising the heat of a biological system damages them beyond repair. So really only one of these is useful in biological systems, and that's catalysts, and that's enzymes. And we'll go a bit more into the specific behavior of enzyme catalysts in the next video.